Hello, everyone. In this video, we will introduce Heap Sort. This is a very interesting approach for sorting. We're going to use a data structure. It's a complete binary tree. It's called a heap. So a heap is a binary tree with the following properties. First, it is a complete binary tree. What is a complete binary tree? A complete binary tree is that every level is filled in the binary tree except the last level. So now this is a complete binary tree, A is and B is, and this one is not, because you have to fill every level except the last one, and the last one and all the elements must be filled leftmost. So this one here, it's open, so that's not. And this D is not, and this level is not filled. So that's first thing is a complete binary tree. The second thing is each node in the complete binary tree is greater than or equal to any of its children. Now for this, and this is and the order property. So we look at the heap, but there's two properties. The first one is called a shape property, it has to have the right shape. The second property is called the order property. So you have to satisfy the order. So the order is here. So for every node and is greater than or equal to its children. And for this, it's 39. And this is not 39, it's less than 42. So this the order condition is not satisfied. So this is not a heap. All right, so here, let's take a look at this animation. So let's insert something here. I'm going to insert 97. So where you put 97, you can put 97 right here. So it will satisfy the correct shape, but the order is not correct. So what do we do is we're going to swap 97 with its parent 50, and then continue to swap it with parent 80. So that is what you're going to see. It's 97 is here. And now let's insert 45. So we're going to put 45 right here. It satisfies the shape property, but the order is not correct. So we're going to swap 45 with its parent 11 and with its parent 43. So 45 is going to be here. So right here. So that is to insert. And when you remove elements from a heap, you always remove the root. Here, the root is 97. So we're going to remove the root. What we're going to do is we're going to remove 97. It's out. And so now you have to fill in something here and to hold the shape. So we're going to put the last one here, 11, to this position. And now it is not in the correct order. So 11 is smaller. And we now look at the children, comparing 11's children here, 45, 80, 80 is the largest. So swap 80 with 11. And the 11 is here. Now swap 11 with 50. And so eventually 11 is going to be right here. So let's do a remove 97 and 11 is here. Now if you remove 80, so you're going to fill in 11 here and swap 11 with 50. So and 11 is going to be here. So this is how you perform remove. And how you perform insert, it's always an insert at the very end. And then perform the adjustment and to satisfy the order property. For the remove, the same thing, you're going to remove it, and then you first satisfy the shape condition, and then make sure the order property is also maintained. So this is the heap. It's also called a binary heap. And this is what you look at it visually. Internally, we are going to store this heap using a list. So now next, and we're going to look at the storing a heap. So we're going to store this. This is the heap right here. This is the heap. So we're going to store this heap using a list. So level by level, and for this binary heap, we're going to have this 62. And this is now, next is 42, 59, and this is 31, 39, 44, 13. And then the rest here, it's all the last level. And this is the one. How do I know who is my parent and who is my left child or right child? So what we do, it's right here. It's a very good property to look at the parent and the left child or right child. So for the element here at this list, so look at the index. So for this index and this position here, I, the left child is 2i plus 1. And the right child is 2i plus 2. And the parent, it's I minus 1 divided by 2. And because this is a completed binary tree, so that's why we can use this simple property. And you can verify, you can prove it. And so, but this is something we going to leave it for you to do a mathematical proof, but we can use that in our algorithm. So now, if you look at this, the parent. So who is the parent index for the element and the index for? So this is the 39. So this, you're going to have this. This is the I, is 4 minus 1 divided by 2. So 4 minus 1 is 3 divided by 2 integer division. It's going to get a 1. So that is here. It's going to be, this is 1. So this is 39. And the parent is 42, 42 at index 1. So who is the left child of the element at 5? So this is 5 is this right 44. So this one is going to be 30. 30 is index is 11. So that's here, 11 right here. And the right child of this 44, it's at index 12. So that's how we store the elements and to discover the parent and the left child and right child for a given element. So we already demonstrated how you add and how you insert. And so you need to discover the parents. You need to find out left child, right child, all this. And so we're going to put all this together in this design for the heap. So we're going to write this code here. So we're going to design this code. This is the one here. It's the heap. And this is my, internally, we're going to use the list to store the elements in the heap. So this is the constructor, and this is add an element. This remove the root. Get size is empty, and peak. And this is get list. Okay, so let's go look at this. Everything here. So this is to get the list right here. Okay. All right, so this is the list. So this is the init method, and in the heap class. So here the internally, so we're going to have this is the empty list to begin with. So this is how you perform add and this is how you perform remove. And so there's some other methods here. All right, we have this, the heap class implemented. So we're going to use this heap class to implement a heap sort. So what we're going to do is to have this is the heap sort. This is the method. So we're going to add every element in the list into the heap. And then afterwards, we're going to remove the elements and put it starting from the end of the list. So because the largest, you keep removing it and put it at the end. And the last one you removed from the heap is you put the first in the list, the bracket 0. So that's it. This is how we write this. So this is the heap sort. And here's the test program for the heap sort. Now, what's the time complexity for this? It's going to be order and log n because it depends on the height. So when you add an element, it's going to take the time that the maximum time is order of the height of the heap. And when you remove it, it's order of the height. So what is the height? The height of a heap is log n. And n is the number of elements in the heap because it's a complete binary tree. So that's here, it's order of log n, it's the height. So you have n elements, so the total complexity for this heap sort. And so you add n elements, it's n log n, and you remove all the elements, it takes n log n, so the total time it's order of n log n. That is all for this section. Heap sort. Thank you for watching. See you on the next video.